Hello and welcome to Compassion. In this video, you will be learning about how to find out number of signals in proton decoupled C13 NMR spectra and off resonance decoupled C13 NMR spectra. So if we want to find out number of signals in proton decoupled NMR spectra, then we need to check how many different kinds of carbon atoms are present in the molecule. And for off resonance decoupled spectra, we need to see number of protons present on the carbon atom, which causes the splitting. So let's solve few problems. So here we need to find out total number of signals in proton decoupled and off resonance proton decoupled C13 NMR spectra. So let's start with this first molecule. If we see this molecule, it is para-disubstituted benzene, and the two substituents present on benzene ring are different. So here if we want to find out total number of different carbon atoms, this is the first carbon which is non-equivalent. Let's say this carbon is A. Then we have this carbon to which methyl group is attached, that will give you second signal. If we see these two carbon atoms, then they are equivalent. So both of them are going to give you one signal with higher intensity. And then we have another set of carbon atom which will give fourth signals of higher intensity. And then we have fifth carbon atoms. That means for this first molecule in proton decoupled spectra, we are going to get total 5 signals. Let's see its splitting pattern. So if we have total 5 signals in proton decoupled spectra, so over here, I'll be writing here. So signal A, where you have methyl group, this methyl group, on that carbon atom, total 3 protons are attached. So based on n+1 formula, where n is number of protons present on same carbon atom, so it will be 3 plus 1, 4. That means it is going to give a quartet. If we see second signal, on that carbon there are no protons attached, so value of n will be 0. That means we are going to get a singlet. Third signal, where you can see on this 1 hydrogen atom is attached. So number of proton present on carbon is 1. That means you get a doublet. Similarly, D signal will also give a doublet. And then we have fifth signal, where there are no protons attached on that carbon atom. So value of n is 0. That means again we are going to get a singlet. So this is the splitting pattern for first molecule. Let's see second example. In second example, we have a symmetrical molecule. We can pass plane of symmetry through carbonyl group. So here, since it is symmetrical molecule, we can consider 1/2 of the molecule and count the total number of signal. So here we are going to get total 3 signals. Say this is signal number 1, 2 and 3. And these methyl group and this methyl group are same, so they will give you one signal of higher intensity. Similarly, this B methylene group, they are same, so they will give you signal of higher intensity. So let's see its splitting pattern. So signal A, which is due to methyl group, on methyl group, you can see carbon contains 3 protons, so value of n is 3 plus 1, that means 4, and we are going to get a quartet. For B signal, over here we have 2 hydrogen atoms attached. It is methylene group. So value of n is 2. That means we will be getting a triplet. And when we see carbonyl group, so on carbonyl carbon there are no proton attached. That means value of n is 0. So that will remain a singlet. It will not split up. Let's see third example. Over here we have two methyl groups, but their chemical environment is different, so both of them are going to give different signals. So we have signal A, then second signal, third is because of methylene group, and then we have fourth signal. So over here we get total 4 signals for this particular molecule. If we see first signal, it is because of methyl group, that means it will be 3 plus 1, so we are going to get a quartet. Similarly, for fourth signal, that is D signal, the other methyl group, again we are going to get a quartet. For carbonyl, that is second signal, since there are no protons attached to carbonyl group, so value of N is 0. That means we will get a singlet. And for this third signal, since there are two protons attached, it is a methylene group, so it will give a triplet. Let's see this fourth structure. So if we see, this is para disubstituted cyclohexane and it is a symmetrical molecule. We can pass a plane of symmetry like this. So over here, if you see, we have these methylene groups, all of them are identical, so they are going to give one signal, and the carbon containing bromine atom will give you second signal. That means total 2 signals will be observed for this particular molecule. As you can see here, it is CH2 methylene group. That means value of N is 2. So it will be 2 plus 1. So we are going to get a triplet. For B signal, second signal, since over here one hydrogen is attached, so value of N is 1. So it is going to give a doublet. And these are the answers. For first structure, 5 signals in proton decoupled, 3 signals, 4 signals and 2 signals. And in off resonance decoupled proton decoupled spectra, we will be getting this kind of splitting pattern for all these 4 molecules. Let's see few more examples. So here, if you can see, we have disubstituted benzene, ortho, meta and para disubstituted benzenes, and the two substituents are again identical. That means these molecules are having certain plane of symmetry. So if we see first structure, it is para disubstituted benzene and substituents are identical. So total number of signals will be first, second and third. We are going to get total 3 signals. So these two carbon are of similar kind, these are of similar kind, so these 4 carbon are going to give one signal, and then these 2 carbons are going to give you second signal, and third signal will be because of methyl group. If we consider ortho disubstituted benzene, we have over here we have a plane of symmetry. So over here we get first, second, third and fourth, total 4 signals will be observed. If we have meta disubstituted benzene, then again here we have first, second, third, fourth and fifth kind of signal. So total 5 signals will be observed if we have meta disubstituted benzene. So these number of signals are possible in proton decoupled spectra if we have identical substituents on the ring. This is similar kind of example. The only difference is here we have methyl group. So like here I explained you, similar kind of signals will be observed over here. And this is how we can distinguish between 3 isomeric compounds using C13 NMR spectroscopy. So over here for proton decoupled spectra, the para disubstituted molecule with identical substituents will give total 3 signals. If we have ortho disubstituted molecule, we will be getting 4 signals, and for meta disubstituted we will be getting 5 signals. If you want to see splitting pattern, so here you can see on aromatic ring, For example, if I consider this first para-substituted methyl group, as I said, we get three signals. So this is signal 1, that is going to give you a quartet. Over here, these two are going to give you a second signal. So 1 hydrogen is present, so that will give you a doublet. And this carbon atom doesn't contain any proton, so that will give a singlet. So we'll be getting total 3 signals. If we consider ortho disubstituted molecule, then these two methyl groups are going to give a quartet. It is a symmetrical molecule. Okay. This carbon is going to give a singlet because there is no proton attached to that carbon. Here one proton is present, so this will give a doublet, and this will also give a doublet. That means total 4 signals will be observed. If we have meta-disubstituted, we can pass plane of symmetry like this. So over here, for methyl group, we'll get a quartet. Then this carbon atom will give a singlet. Here we get a doublet, doublet, and doublet, because 1 proton is attached to those carbon atoms. 1 plus 1 is 2, so we get a doublet. So write the number of signals in proton decoupled and off resonance proton decoupled C13 spectra of following molecule. So over here you can see we have total 4 different kinds of carbon atoms. That means we'll be getting total 4 signals in proton decoupled spectra. In case of off resonance decoupled spectra, this methyl group is going to give a quartet. This will give a triplet, and this will again give a quartet, and this carbonyl will give a singlet. Similarly, for second molecule, we can have total 1, 2, 3, 4, and 5 signals. Over here, this carbon is identical, and these two carbon are identical, so they will give you same signal of higher intensity. So let's see its splitting pattern. This carboxyl group, that carbon will give a singlet because there is no proton attached to that carbon atom. Then we have this next carbon. This will also give a singlet because there is no hydrogen attached. Over here we have 1 proton, so we get a doublet, then another doublet, and a singlet. So this is the answer for first structure: quartet, singlet, triplet, and quartet. And for second we have singlet, singlet, doublet, doublet, and singlet. These are 2 more examples where you can see it is a meta-disubstituted benzene ring, but the 2 substituents are different. So it is not a symmetrical molecule. So when we don't have a symmetrical molecule, let's see how many different kinds of carbon atoms are present. So we get first signal, and this signal will be a singlet because there is no proton attached to that carbon. Then we have another singlet. Then over here we get a doublet and another doublet because these two carbon atoms are different due to different substituents present on aromatic ring. Then this will also give a doublet, another doublet, and a singlet. So over here we have total 7 signals because the 2 substituents present on aromatic ring are different. This example I already discussed, paradise substituted. Here we will be getting a 3 signals, and this is the answer for third and fourth structure. Here few more examples. So let's see this particular structure. Over here we have first signal, first, second, third, fourth, and fifth. So total 5 signal will be observed in proton decoupled spectra, and the splitting pattern in off resonance will be, this will give a triplet because 2 protons are attached to carbon, so 2 plus 1. This will give a doublet, then we have another doublet, singlet, and quartet. Let's see this structure. Since this structure is again unsymmetrical molecule, so we have different kinds of carbon atoms. Let's see how many different carbon atoms are present. So we have two methyl group, but both of these methyl groups are different. So we'll start here. This is first signal, second, third, fourth, fifth, sixth, seventh, uh, sorry, eighth, ninth, and 10th. So total number of signal for this particular molecule are 10 signal. Let's see their splitting pattern. So this methyl will give a quartet because 3 protons are attached. This carbon atom is going to give a singlet because there is no hydrogen attached to that carbon. This carbon will also give a singlet. Over here we have 2 hydrogen, so this will give a doublet. Here we have 1 proton, so over here we have 2 protons, so that is going to give a triplet. Here there is 1 proton, so doublet. This will give a singlet. Then we have another triplet, quartet. Here 2 protons are attached, so 2 plus 1 is 3, so another triplet, and then a doublet. Let's see this particular molecule. Again, this is unsymmetrical molecule. Over here, you might think that these two methyl groups are identical, but actually they are not, because stereochemically, as well as you can see, since there is no symmetry over here, we have carbonyl group. So this methyl group is different from this methyl group. Their chemical environment is different. So let's see how many signals we'll get over here. So we get a quartet, another quartet, and quartet for these 3 methyl groups. This carbon will give a singlet. Over here 1 hydrogen is there, so doublet. Then we get a triplet for carbonyl singlet. Here there is no hydrogen, so singlet, triplet, and another triplet. So we have a 10 signal for this particular molecule. Let's see this example. Here this will give a singlet. Then here 2 protons are attached, so triplet, another triplet, and triplet. So total 4 signal for this molecule. Here we have 2 carbonyl group, but it is unsymmetrical molecule. If we remove this methyl group, then molecule will become symmetrical, and then the number of signal will change. But since we have a substituent, so it is unsymmetrical. So this will give a singlet. These 2 carbonyl will give separate singlets. Methyl group will give a quartet. This carbon will give another singlet, and over here 1 hydrogen is there, so this is going to give a doublet. That means total 5 signals will be observed in C13 of resonance spectra. Then we have this ethyl benzene derivative. So here we get a quartet, then a triplet, singlet. These 2 carbons are going to give a doublet of higher intensity. These 2 carbon will give another doublet of higher intensity, and then we have a singlet. So we'll have total uh, 6 signal for this particular molecule. If we take similar kind of molecule substituents, but ortho disubstituted molecule, so there is no symmetry over here. So this will give a quartet. Then we have a triplet, singlet. This will give 1 doublet, another doublet, 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 and singlet. So we have total 6, 7, 8 signals for this particular molecule. So this is how we find out uh, total number of signals in C13 proton decoupled spectra and splitting pattern using off resonance decoupled spectra. So I hope you understood this. If you have any doubt, you can put it in comment box. Thank you for watching. Please like, share, and subscribe.